Hi, my name is Scott Simpson, and today we'll be talking about the hybridization of atomic orbitals. So we know we have sets of atomic orbitals, and we talked about those in individual atoms, but what happens when we start to form molecules? Well, these atomic orbitals overlap and we get new types of orbitals. Now, there are two types of theories one can discuss. There's a hybridization model, or there is molecular orbital theory. I have a video on molecular orbital theory already, so check that out. Uh, the hybridization is kind of a less complete version of molecular orbital theory, but we still use the same linguistics or similar linguistics to talk about things. And it's widely used in organic chemistry to discuss different types of carbons and nitrogens in a molecule. Okay, so like we said, we have these atomic orbitals, and what happens is the atomic orbitals, remember, orbitals are just a mathematical function. They don't truly exist. They're just a model. So what happens is these mathematical functions, there's a positive and negative overlap between them. They mix together and they form hybrid orbitals. So these guys combine, we get hybrid orbitals. So let's look at an example. Let's consider sp2 hybridized orbitals. Which we'll discuss in a minute what an sp2 hybridized orbital looks like. But what does this even mean? Well, we're talking about the mixture, the formula of atomic orbitals we're using to make our new hybrid orbitals. So what this tells you is we have one s orbital and two p orbitals mixing together to make a new hybrid orbital. So we have one s orbital, and then we have two p orbitals. These guys are going to hybridize, and we get new orbitals out. Now, the number of orbitals in has to equal the number of orbitals out. So we're going to get three sp2 orbitals. So that's what's meant by an sp2 hybridized orbital. If we had an sp3 hybridized orbitals, that would mean we would have one s and three p orbitals all coming together to make our new hybrid orbitals. Okay, pictorially, what does this look like? Well, we know we have a single s orbital, and we know that s orbitals, they're spherical in nature. Then we're going to have two p orbitals, and we know that those look like dumbbells. And the p orbitals actually have a positive and a negative lobe. There's one p orbital. Here's our other p orbital. And we'll color that in. Now, these are all going to mix together. We have constructive and destructive interference. So wherever a red region in this case and a white region meet, we'll say this is positive, this is negative. They're going to cancel each other out, just like destructive interference from a wave. And wherever we have similar signs meeting, we're going to get constructive interference. So these guys are going to hybridize. And we can change the sign of these. We can flip the sign to get all possible combinations. And what ends up happening is we get three orbitals. One like that. One at this angle. One at that angle. And we'll color those parts in. Okay, so we have these three new orbitals. Now let's take, so these are our three sp2 orbitals. We have our two p orbitals and our s orbital that we use to make these three sp3 orbitals. Now let's combine all those sp3 orbitals together and let's see what we get. So combining, which I just totally butchered, combining our sp two orbitals. So let's smash those together. So we're going to mix all these guys together, starting at the same point. And what ends up happening is 1, 2, 3. This is the combination of all of those sp2 orbitals. And if we measure this bond angle around here, I bet you can guess what the bond angle will be. It is 120 degrees. And if you look, what electron pair shapes have that bond angle? Generally, trigonal, planar electron pair shapes, or electron domain shapes. So if we know the electron pair shape or the electron domain shape, we know the number of effective pairs, you can actually determine the hybridization of any atom in a system. So let's talk about determining hybridization. Determining hybridization. So it's based off of the electron pair shape, or some people call it the electron domain shape, and the number of effective pairs. So based on number of effective pairs, where if you're not sure what those are, I have another video outlining how to determine effective pairs. So check that out. And electron pair shape, or electron pair geometry, or electron domain geometry. It goes by a handful of different names. Of course, everything has to be confusing, right? Okay, so what we're going to do, we're going to make a table. We're going to keep track of the number of effective pairs. We're then also going to keep track of the electron pair shape. And then we're going to keep track of the hybridization. So what type of orbitals are constructed when we let those atomic orbitals overlap? We're going to discuss 2, 3, 4, 5, and 6. So if you're not sure what the electron pair shape would be, you should go back, review it. I again have another video on that. Feel free to check that out. We know if we have 2 effective pairs, we have a linear electron pair shape. 3 effective pairs we just talked about, trigonal, planar. 4 effective pairs would be tetrahedral. 5 effective pairs gets us trigonal bipyramidal. And 6 gets us octahedral. When it comes to the hybridization, if we have 2 effective pairs, that means we have 2 atomic orbitals overlapping. We get sp. For 3 effective pairs, we got to introduce another atomic orbital, sp2. 4 effective pairs, sp3. Now you might be thinking 5 effective pairs, let's do sp4. The problem is per n, or per energy level, when we're discussing those quantum numbers, we only have 3p orbitals, so we have to use another orbital in the mix. The next lowest in energy orbital would be a d orbital then. Therefore, for 5 effective pairs or a trigonal bipyramidal electron pair shape, it would be sp3d. Then if we go to octahedral, you can guess sp3, we're going to increase the number of our orbitals by 1, sp3d squared. So if you look, you can use this to try and determine what is the hybridization at any point in the molecule. That becomes increasingly important when we're discussing bond topologies in organic chemistry, and even in inorganic chemistry. general chemistry, we commonly refer to these atoms or different sites as an sp2 hybridized carbon, an sp3 hybridized carbon, and so on. That way it gives you an image in your head and you know what we're discussing. Okay, so let's look at an example. We want to determine the hybridization of each atom in the following molecule. So this is our molecule. Now we have to consider the number of effective pairs around each atom. Hydrogen is a little tricky compared to some of the others. If we think back to the only available orbital for a hydrogen atom, it's an s orbital. So all of these hydrogen atoms, they're all hydrogens. They're just an s hybridization. They have no other orbitals that overlap. Now let's consider the carbons. Let's label this one carbon A, this one carbon B, and we can leave the nitrogen just as nitrogen because there's only one of them. So now we have to determine the number of effective pairs around carbon number A. If we look, remember, double bonds are worth one effective pair. So we got 1, 2, 3. That means that carbon A has 3 effective pairs. We know that means a trigonal planar electron pair shape, which also means that we have an sp2 hybridization. So this carbon right here, it's an sp2 hybridized carbon. Carbon B, if we look at that one, we do have this hydrogen sitting up there, 1, 2, 3, 3 effective pairs. We're going to have the same situation. It's an sp2 hybridized carbon. Now, what about that nitrogen? Remember, it's based upon the lone pairs. So the nitrogen, let's count, or excuse me, effective pairs, not lone pairs. Let's count how many effective pairs we have. We have 1, 2, 3, and remember, that lone pair there counts as one effective pair. So we have a total of 4 effective pairs. Since we have 4 effective pairs, that means we have a tetrahedral electron pair shape, meaning an sp3 hybridized atom. So this would be an sp3 atom, as I hit the camera. Okay, so remember, those lone pairs are important. To show another example, let's look at formaldehyde. Okay, since these are hydrogens, we know the hydrogens are only an S hybridization. That carbon has 1, 2, 3 effective pairs around it. It's an sp2 hybridized carbon. The oxygen, remember, lone pairs count. We have 1, 2, 3 effective pairs. So that would be an sp2 hybridized atom. So be sure to look at and count the number of effective pairs. It really is just that simple. Keeping that in mind, you'll be able to gauge what these systems look like by just hearing the words, it's an sp2 hybridized or an sp hybridized carbon. Okay. With that, I'd like to thank you for watching. If you have any questions or concerns, please leave a comment below or feel free to contact me. Thank you.